Okay, so today I'd like to talk about Stephen Hawking's black hole theory, and I looked up a few articles. I have a PowerPoint slideshow from Santa Rosa University students. I have his actual write-up on his findings, and then I also have his more layperson article. It's actually a lecture, but it's written down, so it's sort of like an article. But so what I want to start with, and this is from the Santa Rosa students' PowerPoint, is how black holes are formed. And so what you start with a nebula, which is basically a star nursery, and all the gases will eventually, as more come together, gravity increases, and you create a star. And then you start with a sun-like star, and then as sort of the sun-like star loses energy and grows older, it sort of spreads out and becomes dimmer, and that's what they call a red giant. And then you get planetary nebula, which are, you still have not totally, it's a little unclear, but it's also like the nursery, the star forming nebula, but you can get planets out of it as well, or you can get a white dwarf star, or that'll just go back to a star forming nebula. And then after that you can get a massive star, which this is the same cycle as a sun-like star, but with larger stars. And then so after a massive star, you get a red supergiant, which can turn into a supernova, which has 3 other paths it can take after a supernova, which is a star-forming nebula, a neutron star, and a black hole. And so what we're interested in is black holes, because that's what we're going to talk about today. And one thing I'd like to clear up with black holes is they're often depicted as these two-dimensional holes in space, but because space is a three-dimensional, well, it has 3 dimensions that we can move in. If you look at the hyperspace theory, there's potentially 10, so that all the forces in the universe that we know can coexist, but that's for a different time. A black hole would actually look more like a sphere, in which from any side you have an event horizon, which would also be curved around it. Because to have a 2-dimensional object in a 3-dimensional space doesn't work unless it's an absence of something, and a black hole is very definitely something. So what I'd like to talk about now is Stephen Hawking believes that a black hole can actually emanate information very slowly, but with a progressive exponential curve. As more information is lost, the mass of the black hole goes down, and that allows more information to escape faster. And then eventually the black hole will fade away into nothingness, and the information will be released. And in his actual write-up of his findings, he says that it would be too scrambled to actually glean anything from it of what the inside of a black hole is like, or what it looks like, or how it works. And so the way he thinks that black holes can emanate information and like radiation is they have the location of a given particle very precisely inside a black hole, because it's a singularity. It exists in only one point, so everything inside of it must exist in that one point. So because you know the position very accurately, and due to quantum mechanics, the more exactly you know the position, the less accurately you know the speed. And when you know the position to that level of precision, you don't know the speed, and that allows the particle to move faster than the speed of